Okay, so however, this is a workshop on Olympiad number theory by DMV Math Circle. So, number theory is really important for both Olympiad math and math beyond competitions. So, in this workshop, we're gonna go over some theory, which can include orders, Euclidean algorithm, and how to apply it on problems, and then quadratic reciprocity and prime exponents. And we'll also go over some problems which I thought were very instructive. So, and at the end, there are also some high quality questions that you should try, and they're from various contests. So the first question we'll go over is a question from AIME in 2018. So it says that to find the least positive integer n, where when you write 3 to the power n in base 143, the two rightmost digits are 0 and 1. So the first thing you want to do when you try to approach this question, what does the two rightmost digits being 0 and 1, what does that really mean about the number? So the other digits in the number in base 143 will all correspond to parts of the number that are divisible by 143 squared. So the 0 and 1 basically just implies that the number is going to be 1 mod 143 squared. So now what you want to do is you should prime factorize 143 as 11 times 13, which all of you should know. Yes, that is true. You do want to order, but we're going to go over how you're supposed to find that. So you have 3 to the n is 1 mod 11 squared times 13 squared. So basically any n where 3 to the n is 1 mod 11 squared and 1 mod 13 squared will satisfy the condition, and which is basically what we're trying to look for. So the first case is when 3 to the n is 1 mod 11 squared. We can simplify this to, first we have 3 to the n is 1 mod 11, which we can then extend that to get 3. So we have 3 to the x is 1 mod 11. So, and we want to find the smallest x for which this is true. So I'm gonna so you can look at small n. We have 3 to the 1, 3 to the 2, up until 3 to the 5. But 3 to the 1 through 3 to the 4 are not going to be 1 mod 11, but 3 to the 5 is. So therefore the smallest n, where 3 to x is 1 mod 11, is just n equals 5. But so now how can we find all n where 3 to the n is 1 mod 11? You can message in the chat. So like, well, what must x satisfy if 3 to x is 1 mod 11? Yeah, so 5 has to divide x. And the reason why is you'll have 3 to the x is equal to 3 to the x times 3 to the 5 mod 11, because 3 to the 5 is 1 mod 11. So it'll be equal to 3 to the x plus 5, which means that since 5 works, you'll have 5 works, so then 10 works, and so on. And then since 1, 2, 3, and 4 don't work, numbers that are 1, 2, 3, and 4 mod 5 won't work either. So x has to be a multiple of 5. So by that logic, you get n is to be a multiple of 5. So you can write n is equal to 5k. So you have 3 to the n is equal to 3 to the 5 to the power k. So now you want to take this mod 11 squared. So the first thing you should try is obviously to take 3 to the 5 mod 11 squared. What's that going to be?
Arnav! Wait,
Yeah, so as Christopher had said, 3 to the 5 equals 243 is actually 1 mod 11 squared. So one can take 243 mod 11 squared, and you'll get 243 to 3 to 5 to the k, which is 243 to the power k, is going to be 1 mod 11 squared. So then that means that if n is a multiple of 5, then 3 to n will have to be 1 mod 11 squared, no matter what k actually is. So for this case, the answer is going to be 5 divides n. So now you have the other case, which is more interesting, where 3 to n is 1 mod 13 squared. So now what's the smallest n where 3 to the n is 1 mod 13? This is, you can message in the chat. Yeah, so the answer is 3. So you can see that 3 to 1 is 3 and 3 to 2 is 9. Those are obviously not 1 mod 13. But 3 to 3 is 27, which is 1 mod 13. So this means that 3 has to divide n, like with a similar approach from the other case. So now if we keep going, we can set n equals 3 to the k, and you have 3 to 3k, which is 27 to the k, has to be 1 mod 13 squared. So for this part, there's a really nice way to apply the binomial theorem. And this is motivated by the fact that 27 is equal to 26 plus 1. So if you were to write 27 to the k as 26 plus 1, all of the quantity of that to the power k. So I'm using the binomial theorem because we haven't, you can use, there's a thing called LTE that you can use, but we're not going to use that for this. So you have 26 plus 1 to the power k. So all of the terms will have at least 2 powers of 26, except for the ones given by 26 times, well, except for the ones given by k choose 1 times 26 plus 1. So this number has to, which is just 26k plus 1, has to be 1 mod 13 squared. Well, this means that 13 squared has to divide 26k. So k has to be multiple of 13. Yeah, binomial theorem is actually a good way to solve a lot of modular equations. So now what does this imply about n? If k is multiple of 13 and n equals 3k. You can say in the chat. I assume you meant 39 divides n, but yeah, so yeah, 39 has to divide n because 13 divides k and n is equal to 3k. So now we have, so from the first case, we had that 5 has to divide n, and from the second case, we have the 39 has to divide n. So what does this mean now that, so what number in general has to divide n? Yeah, so since 5 and 39 are relatively prime, n has to be multiple of 5 and 39, and we just proved, yeah, I know you said that. So n has to be multiple of 5 times 39, which is 195. So that's the answer to your question. So now we're gonna work through a little bit of orders. So basically, it's important for any positive integer x and a prime p, to look at how the cycle of powers of x, how it cycles and works. So we can see, so we want to find when it hits 1, because after it hits 1, when you multiply by x, the cycle of powers of x is just going to repeat. So it's the smallest positive integer d, where x to the d is 1 mod p. So if x to the n is 1 mod p, for some n, what must d satisfy? Yeah, d has to divide n. So one way you can prove this is, so you suppose that if d didn't divide n, what you can do is you get that GCD of n and d has to be less than it. I mean less than d. So you're gonna find integers a and b where an minus bd is equal to that GCD. But you get that x to the power of that GCD of n and d is equal to x to the power of a times n over x to the power of b times d. However, both x to the a and x to the bd have to be 1 mod p. So the quotient also has to be 1 mod p. But this means that x to the x to the power GCD of n and d has to be 1 mod p. So GCD of n and d has to be greater than or equal to the order. But this is going to be impossible if d doesn't divide n. So yeah, so now we have some number n where x to the n is 1 mod p. And the simplest example of this always being true is when n equals p minus 1. So we get that so all the orders have to divide p minus 1. So some next number, there's always going to be some number where the order is going to be exactly p minus 1. These are called primitive roots. They're really important because every positive integer that's not multiple of p, every remainder mod p can be given by a power of a primitive root. So for example, if you have some number, you can always rewrite it as g to the power k for some primitive root g. And you can alternatively write it as the set of g to the power 0, g to the power 1, and up until g to the power p minus 2 in modulo p is the same as this 1, 2 up until p minus 1. So now we're going to solve a question that has to do with this idea. So this question at first kind of looks a little annoying to approach because all the bases are different, and it seems hard to get a sum for all n. Because even when you know that, so one thing you can do for odd n, it's pretty simple because you compare a to the n with p minus 1 to the n. I mean, but this doesn't exactly work for even n. This doesn't easily work for even n. Yeah, p is prime. So what's one way to make the exponents, I mean, the bases all the same in this question? Yeah, so you can use g in this, and as I said earlier, the set 1, 2 up until p minus 1 is just going to be the same set as g to the 0 up until g to the power p minus 2. So here's the expression you have. So now you have this. So you now have this sequence. So it's going to be, as people said in the chat, it's a geometric series. This is not UCMO. So yeah, you have a geometric series with ratio g to the n in first term 1. So the sum should become g to the power of n times p minus 1 minus 1, which is, and then over the ratio minus 1, so g to the n minus 1. So, when will this not be defined in general? Because yeah, so if n's a multiple of p minus 1, then you'll have g to the n minus 1 is going to be 0 mod p, but you can't really, even in mod, you can't divide by 0. So if g to the n is going to be 1 mod p, so p minus 1 divides n, you can directly just solve for f of n because it'll be the sum of p minus 1 different numbers that are all required to be 1 mod p. So it has to be p minus 1 mod p, and you can write that as -1. And the other thing is when g to n minus 1 is not 0 mod p, you can directly evaluate this sum. So of course, g to the n times p minus 1 has to be 1 mod p. So -1 has to be 0 mod p. So f of n is going to be 0 mod p. So to sum up, the final answer is going to be 0 mod p if p minus 1 doesn't divide n, but it's going to be -1 mod p if p minus 1 does divide n. Okay, so now we're going to talk a little bit about kind of the Euclidean algorithm and a problem involving it. So this is not very theory based. It's more just the idea of, so if A divides B, then A has to divide any like integer linear combination of A and B. And if you can find something that's small in general where, so for example, like B is equal to 2A plus 3, you can get the A has to divide B minus 2A, which is 3. And so since A divides 3, A has to, if A is positive, A has to be 1 or 3, and that's a pretty good restriction on A. So the question we're going to go over is from 2011 AIME Shortlist, and so you have an odd integer n. This is going to be important, and you want to find all functions over the integers. So mapping an integer to another integer, such that for all integers x, y, you have f of x minus f of y has to divide x to the n minus y to the n. Yeah, so this is a trick that in functional equations that makes your work easier. Yeah, so as Ben said in the chat, so if f works, then f plus any constant has to work, which means yeah, you can assume that f of 0 equals 0. Yeah, like a derivative. That's right. And you can add all of your solutions. Like once you get a set of solutions, you have to add it by any constant c. So now it makes sense to, well, we can make a shorthand for plugging in numbers to the equation. So essentially, setting x is equal to a and y equals b is going to be denoted as p of a comma b. So if you have f of 0 equals 0, what's the most logical assertion you can plug in, you can make into the equation? Yeah, so y equals 0. Yeah, so you have f of x has to divide x to the power n. Yeah, so first you can, so first the easiest thing to do is where x to the n has the least number of divisors, which is true with x equals 1. Yeah. So you have f of 1 and f of negative 1 are going to be in negative 1 and 1. Now as Harry said in the chat, you can, another number that's importantly has not too many divisors is going to be a prime. So if you have x to the prime p, right, you have f of p has to divide p to the power n. Now this means that an absolute value of f of p, because f of p has to be either power of p or negative f of p has to be. So the absolute value of f of p has to be something in between p to the 0, p to the 1, up until p to the n. So now the idea in questions with divisibility functional equations, if you can find, say, some number where, or some function where, some nice function, maybe a linear polynomial or something where there are infinitely many x that satisfy that f of x is actually going to be equal to this function. The idea is you can make a plugin where with y is equal to one of these numbers and try to find a linear combination where the left-hand side will include one of these numbers that can be hit infinitely many times, but the right-hand side only includes something in terms of fixed x. So we'll see how this works in this question. So since absolute value of p has to be power of p, we can, and there's only n choices of the exponent in general, or n plus 1. There's a finitely many possible choices of the exponent. We can also choose some exponent that's going to be hit infinitely many times. just because there's infinitely many primes phi high. So suppose that, say that it's going to be p to the power d. So you have two cases where the first case is going to be f of p is equal to negative of p to the power d for infinitely many p. So what's some logical assertion to make in the equation? And for people, for reference, I can write down the equation here. So people can see it's not going to be that neat, but. So f of x minus y. Wait, this is not what I wanted. So it has to divide x dn minus y dn, yeah. So yeah, I can do type the text, but yeah, so I mean, they're going to be infinitely many primes where this is not true, but you can really focus on the fact that the function negative p to the d has infinitely many values where f is equal to this function. So if you, for example, plug such primes p, so you'll have x to the power f of x plus p to the power d is equal to x to the n minus p to the n. So what you're trying to get here is a linear combination of the left-hand side and the right-hand side of this divisibility, where the left-hand side, the left-hand side, which is going to be f of x plus p to the power d, has p inside it, but the linear combination shouldn't have a p inside it, and only be in terms of x, n, and p. Yeah, that's basically what you do. So what's a possible linear combination that won't have any p inside it? Well, so the first thing you might try would be to multiply the left-hand side by p to the power n minus d, but that's slightly annoying because the f of x will then get powers of p. But yeah, but now you can do something else. If you have, for example, if you have some numbers a and b, you can get like a plus b has to divide a to the n plus b to the n. Wait, multiplying by that might work, but it's probably basically the exact same idea. So the way you can do it is where f of x plus p to the d. So you has to divide f of x to the n plus p to the d to the power n. And the reason why is because is because n is odd. And you're gonna have a plus b divides a to the n plus b to the n for any odd n. So, and similarly, you can this is how you can get p to the power of nd for this one. However, you can also get p to the nd from the right hand side. So you can take both x to the n and p to the n to power d. So you'll have x to the n minus p to the n divides x to the nd minus p to the nd. well, a minus b divides a to the n minus b to the n for even n. But this is, I mean, but a plus b doesn't have to divide a to the n plus b to the n if n's even. But since n is odd, as said in the question, you can now sum these two numbers, f of x. You can sum these numbers and you get a linear combination of the left hand side and right hand side. So you get f of x to the n plus x to the power nd. And so if if f of x plus p to the d has to divide this number, which has nothing in terms of p, what can you say about f of x to the n plus x to the nd? If it's true for all such primes p, of which there are infinitely many. Yeah, so it always divides, and then so what will that imply about the right hand side? Yeah, so the right hand side has to be 0. And the reason why is you can see. So f of x plus p to d has to divide the right hand side, and it's true for infinitely many p. So now simplifying, you get f of x to the n is negative x to the nd, and since n is odd, you get f of x is negative x to the d. So this was the first case where f of p is equal to negative p to d. So now we have the yeah, so we have to, so that's one solution, but not necessarily all these work. So this is what the equation becomes. So for which d and n is this true? Yeah, so it's for divisors of n. You can actually nicely prove this. So if you have x to the n is equal to y to the n mod x to d minus y to d, you also have that the numbers x to the d and y to d have to be the same mod x to the d minus y to d. And now since x and y are coprime, you can divide both sides. So now you get that x to the d minus y to d divides x to the n minus d minus y to the n minus d. So now what happens if you like repeatedly apply this? So if you repeatedly apply this, what you can get is x to the d minus y to d divides x to the r minus y to r, which is, and r is just n minus k times d for some k. And you can just choose k where such that this becomes the remainder when n is divided by d. So since r is less than d, this looks to be an easy size contradiction. And this is right. So a simple way to do it is just by setting y equals 1, because the left-hand side is always going to be the greater than the right-hand side for x greater than 1. So, I mean, this is going to be, and so this is always going to be 2. So this means that the right-hand side is going to have to be 0. Because both sides are going to be non-negative. So, and this obviously means since x and y are not equal, this means that r has to be 0 and therefore d divides n. Now from this idea how a minus b divides a to k minus b to k, all d divides n also has to work. So now we have the similar case. So, but we have like f of p is equal to p to the d. So now what's possible linear combination of f of x minus p to the d and x to the n minus p to the n won't be what possible linear combination is not going to be in terms of p. Yeah, it's basically the same thing. So except instead it's going to be f of x to the n minus p to the nd, and then x to the nd minus p to the nd. So you can, yeah, you can also say that, but I'm just gonna go. It'll also be this. is the same size contradiction. So instead of adding, you can subtract. So basically the same idea. You get to the right hand side of this, which is f of x to the n minus x to the n d. We'll have to have infinitely many divisors, so it's 0. So f of x is now x to the d. So similarly, we have the exact same divisibility, and we know this means that d has to divide n. So now what are our solutions to the equation? Yeah, I agree, this is a fire problem. Yeah, so we have our solutions. We're going to be, yeah, powers of x to the d for some d dividing n. And then at the end, we shifted by a constant. Well, d equals 0 isn't a problem because that would imply that f is constant at 1, and the left-hand side is going to be 0, but the right-hand side's going to be non-zero for most x and y. Yeah, it'll be the same size contradiction when d equals 0. Okay, so now we can move on. So this is going to be a little about quadratic reciprocity. So this is essentially the study of figuring out which values of x can give a value of t where x is t squared mod p. But we'll use a little bit of orders in this. So what has to be satisfied about the order of quadratic residues mod p? Yeah, so the order, well, it has to divide p minus 1 over 2, that's not necessarily equal. Yeah, primitive roots there are non-quadratic residues. So to prove that this has to be true is the same, say d is the order. You get like x to the d is t to the 2d. And if this is 1 mod p, this means that 2d divides p minus. This means that since so this means the order has to be divided by p minus 2. Or p minus 1 over 2. So you can also prove the reverse direction, that anything with order dividing p minus 1 over 2 also has to be quadratic residue. So this is the same, this idea which I talked about how primitive roots are really important. So if you have x to the p minus 1 over 2 is 1 mod p, you can write x as d to the power k, and what happens is the exponent of g is going to become k times p minus 1 over 2. But for this to be 1 mod p, it has to be multiple p minus 1. So then k is even, and therefore x is perfect square. I mean, perfect square mod p. Hi. Yeah, so now there's a symbol that will, the Legendre symbol that'll determine which numbers are. Yeah, I actually can turn on my camera. Which will determine whether a is a quadratic residue mod p or not. And it's defined by basically a to the power p minus 1 over 2. And that taken mod p. So as we've shown earlier, if a is a quadratic residue, this number is going to have to be 1. I mean, if it's non-zero. And then if it's okay, we'll flip it out now. Okay, so and then 0 if a is a multiple of p, and then Now, finally, if A is not going to be a QR, so why would, if A is not a QR, why does A to the power p minus 1 over 2 have to be a negative 1 mod p? Yes, you square it, you get something that's 1 mod p, and this is for non-quadratic residues. And since we've proven it can't be 1 and its square is equal to 1 mod p, it has to be negative 1 mod p. So that's why a non-quadratic residue will have to have this symbol go to negative 1. So here's some properties. So the first one is, well, this is taken directly from the definition. And a way to simplify it is where negative 1 is a quadratic residue if p is 1 mod 4, but it's not going to be a quadratic residue if p is 3 mod 4. Now the one about 2. This one is difficult to prove, but it's usable in contests. So this is equivalent to where 2 is a quadratic residue if p is either 1 or 7 mod 8, but it's not a quadratic residue if p is if p is 3 or 5 mod 8. So this is going to be important. So now the most important rule is probably this is the p I forgot p has to be odd, and p has to be an odd prime. So the log quadratic reciprocity is the third one, and yeah. So this is just where you can relate p, or the symbol when p over q and when q over p, you can relate them depending on what q and p are mod 4. So if q and p are going to be both 3 mod 4, then they're going to be opposites of each other. And otherwise p over q is going to be the same as q over p. So there's basically when either of them is 1 mod 4. And they have to be distinct. Okay, yeah, Jacobi symbols are better, but yeah, but that's basically just a multiplicative extension of both the numerator and denominator. So yeah, so the fourth property is, this is also basically direction of definition, where the product of a the symbol of a over p and the symbol of b over p is going to be the same as it is for ab. So and the proof of this is going to be, this is just directly from the fact that a to the p minus 1 over 2 times b to the p minus 1 over 2 is just ab to the p minus 1 over 2. So this is, in fact, I think this will imply that the product of two quadratic residues is a QR. Then the product of two non-quadratic residues is also QR. But when you multiply quadratic residue and a non-quadratic residue, you'll also get a quadratic non-residue. So yeah, so there's a question that uses this idea pretty well. So if we're trying to prove that the sequence has, well, so first the question is that the sequence an has to be divisible by, there has to be some element in the sequence for every prime number greater than 1402, it's a random number, such that that element's a multiple of that prime. So you don't need Kobayashi for this question. So if we're trying to, and now we're trying to prove that there's infinitely many primes that divide some element of the sequence Bn. It can be different elements for different primes. So the first thing we obviously going to do is suppose that this was not true, and only finitely many primes divided some element in the sequence. So now, so now look, what can you say about certain primes that divide elements in Bn? Or in another way, so how many elements in the sequence like can primes divide? Or how many do they have to divide? Oh yeah, I'll explain it real clear. So the idea is that if only finitely many primes has to divide elements in the sequence, but there's infinitely many elements in the sequence, so there has to be some prime dividing infinitely many elements in the sequence. So if you and this can be very important. So so now what has to be satisfied about primes that divide infinitely many elements? Yeah, so they can't divide any element of an. So what does this mean, like combining this with the condition of an? Yeah, so any prime that divides infinitely many elements has to be smaller than 1402. Yeah. So now when you have some sequence with finite number of prime divisors, you can also look at the prime divisors that are divisors of elements of the sequence. So there has to be, there can only be finitely many of these by our assumption. So now what happens is, so now what happens for if what happens for if an eventually? So how does the sequence work eventually with respect to these prime factors? Yeah, there's an AI where P divides AI for every large enough P. So any prime over 1402 has to, it can only divide finitely many elements of the sequence. So of the sequence Bn, for large enough n, what are going to be what are the only divisors of the sequence? Prime divisors are. So it has to be prime divisor smaller than 1402 because at some point there's only finitely many primes that divide finitely many elements of the sequence. So at some point, all the primes greater than 1402 will stop to divide elements. Will stop dividing elements in B. So we can rewrite this as an equation where B of n is just the product of powers of primes less than 1402 for large enough n. Yeah, so primes don't, oh, yeah, that's because for large enough n, it's going to be -1, so they can't divide infinitely many elements. I mean, oh shoot, I meant the largest prime under 1402. Yeah, so that's PK is the largest prime under 1402, and I can change this now. Yeah, so it's the largest prime under 1402. So now like for no, we do not need to find a value for PK. Because remember, 1402, it is just some arbitrary number. You can replace it with anything. So okay, so PK is gonna be, well, yeah, PK is gonna be 1399, I guess. Yeah, so yeah, yes, we indeed can replace it with 1434. Yeah, so if you continue on, you can look at primes greater than 1402, and so what does B of n has to how does it eventually have to be modulo P? Oh yeah, so I said that what is B of n eventually modulo P for primes P greater than 1402? Yeah, there's nothing special. Well, not one, it's gonna be A1 times A2 up until AN, but then -1. So what will I evaluate 2 in mod P? Where P is some prime large enough prime greater than 1402. Okay, so here, so basically it's gonna actually be -1 mod P. So P has to divide, so we can choose n where P divides A1 times A2 up until AN. And we can choose n since this is gonna be large. So n's gonna be large, so then B of n has to be a product of primes less than or equal to 1402. So some product of primes less than 1402 is gonna be -1 mod P for all sufficiently large primes P. Like, so you want to choose P where this is not possible. So now going back to the point of this, or this stuff I'd covered earlier before this question. How can we use choose P where this is not true? Um yeah, the Jacobi thing is right. So you can use quadratic reciprocity to do it. Yeah, so so you want that well, yes, you can make either the left-hand side of QR and the right-hand side and a non-quadratic residue. So yeah, so you want the left-hand side to be a quadratic residue and the right-hand side not a quadratic residue. So yeah, so of course we need to have P is equal to 3 mod 4 for. So these are symbols that'll all have to equal 1. So 2 of P up until PK of P, are all gonna have to be 1. And then you also need -1. The symbol of -1 in P has to also be -1. And that gives p 3 mod 4. So now the 2p condition is from the theorem gives that p is either 1 or 7 mod 8, but since it's 3 mod 4, also has to be 7 mod 8. So that's one modular condition that you need. So now how do you think you can make the other Legendre symbols equal to 1? So you want 3, 5 up until p and k all to be quadratic residues mod p. How could we choose p for which this is true? Wait, we know p is greater than 1402, but in terms of the primes, less than 1402, what could we? Or let me go back a little bit. So if q is a quadratic residue mod p, what does this say about p mod q using the law of quadratic reciprocity? Yeah, so what does this say about what does this say about p over q? Well, it's one if q is it's gonna be one if q is 3 mod 4 and okay, one is q 1 mod is q is 1 mod 4 and then -1 if q is 3 mod 4. So yeah, so you got a congruency for p in terms of modulo q. And this is basically the proof that such a congruency always exists. All you need to show is that there's a quadratic non-residue and a quadratic residue. So an example of a quadratic residue is just going to be 1. And an example of a quadratic non-residue is just going to be, for example, like what's an example of a non-quadratic residue? Well, q minus 1 could be a quadratic residue if q is 1 mod 4. Oh yeah, well, okay, yeah, that's right. Q is 3 mod 4. Yeah, so q minus 1 does work. The other one I was thinking was a primitive root too. So you can always find some residue for every q where q is going to be a quadratic residue mod p. Oh yeah, Arnav, the person whose nickname Arnav Iyengar is Oren. So yeah, so now as Louis had said, you can you cannot do a CRT argument because 8 as well as all the primes q are all relatively prime to each other. So you can find some prime p where all of these Legendre symbols are going to be equal to 1. And like we need p to be greater than 1402. And there's there's going to be infinitely many numbers that satisfy the modular congruences. So choosing such p and taking mod p will give a contradiction. And this means that this means that sequence B has to have infinitely many prime divisors. There's a lot of other questions that are about this infinitely many primes divisor thing. But I thought this was a nice way to use quadratic reciprocity. Okay, so this next thing we're going to talk about is the p-adic valuation, which is just if you look at the prime factorization of a number and you take the exponent of a prime p. So this can be 0. This could also be something greater than 0. So if you have 48, it's just going to be 2 to the 4 times 3. So the v2 is going to be 4. So another nice thing is that this can be, you can use this in rational numbers too. And something really cool about this is if you're trying to prove that, so you know, proof that square root of 2 is proof that square root of 2, for example, or cube root of 2 is going to be irrational. This a very simple way to get it is by supposing the square root of 2 is going to be equal to m over n, and then using v2 to get a contradiction. Yeah, I'm not going to prove it. So yeah, so you have vp of m over n is just vp of m minus vp of n. And this will, and so, I mean, the vp is really important because if a divides b, vp of a has to be less than vp of b. So we can clearly also find a vp of the sum of, usually we can find a vp of sum of two numbers and a difference. Yeah, the last question will be a little bit more difficult than the rest. So yeah, so if vp of m is greater than vp of n, we get the vp of n plus 1, n has to be vp of n, just because any prime power dividing, any power of p dividing m and n, I mean, also has to divide n, but any prime power divide that doesn't divide n, that divides m, it'll divide m, but it won't divide n. So, and then similarly, if the same thing holds if vp of m is less than vp of n, and if they're equal, the vp of m plus n has to be at least vp of m, but we can't tell the equality holds. So, like an example is v3 if 3 plus 24 is going to be 3, but v3 of 3 and v3 of 24 are both equal to 1. So now we have a final question from the China TST, which is, this is like a combination of two functional like equations, but written as a sequence. So for any distinct, which is important, positive integers m and n, their GCD has to divide am squared plus an squared, and then the GCD of am and an has to divide m squared plus n squared. And it's asking us if there's some k where there's 2019 positive integers where a of k is equal to a. So for this question, it makes sense to start by trying to find all k good numbers, or try to come up with such a characterization. Oh yeah, I did see it. Yeah, so yeah, so we could, so yeah, so first we look at the first equation where m and n are clearly going to be multiples of GCD of m and n. So if we fix some d as the GCD for any m and n that are multiples of d, yeah, you can look at this through VP also. So yeah, sort of forces. Yeah, so d has to divide the sum of am squared and an squared, where m and n are any different multiples of d. However, what if you just take 3 multiples of d? And this means that for any m that's a multiple of d, am squared has to be the opposite in mod d of an squared. So this means you'll have three numbers where their squares are all going to be opposite to each other. So we can see that this obviously means that they all have to be equal mod d. So yeah, so you have like HUDs. You don't necessarily have to use quadratic reciprocity for this question. But you have that you let that A of D and A of 2D have to be the same mod D. I mean, their squares have to be the same mod D. So D actually has to divide 2 times A of D squared. This is really important because if you look at VP, it means that as the VP of D grows large, the VP of AD also has to grow large. In a way. So it has to grow similarly at least to the VP of D over 2. So yeah, so this is the VP notation. So now here's a funny way I found the motivation of the well, yeah, VP of 2 is gonna be 0 for P not for P greater than 2. So you almost have something like D divides A of D squared, but there's the annoying factor of 2. So one way I could work around this. So it's really nice if you could possibly set n equals 0. This is the way I thought about it. Because if you were to set n equals 0, you get the m divides A of m squared, and then A of m divides m squared. So it looks like that's probably what you're gonna be looking to prove. So instead of setting, so if you set n equals 0, this means that you're getting this VP result for all primes P. But instead, what you could do is get it for individual primes P and then combine. So now if you keep going. So you can choose n, where the VP of n is going to be really, really large. So if you go into the first equation, so GCD of m and n, the VP of this is going to be the minimum of the VP of n and VP of m, which is going to be just VP of m. And then the right-hand side is going to be the VP of am squared plus an squared. And then since we can choose VP of n sufficiently large, where VP of an squared is greater than VP of am squared, we'll get VP of an exceeds VP of am. So we'll have VP of m, since GCD of m and n divides the sum of the squares of am and an, VP of m has to be less than or equal to VP of am squared. And this is true for all primes P. So m has to divide am squared. So now if you look back at the equation and try to solve this for instead the second equation and choose n the exact same way. So what does the VP of the left-hand side become? You can send it in the chat. Yes, you're choosing n with VP of an is greater than VP of am. So what's going to be the VP of this GCD of am and an? Well, close, but yeah. So wait, let me write just so m and n don't look confusing. I'll write what I had meant to say in the chat. Wait, never mind. It's gonna be like this. So it'll look like this. So the left VP of the left hand side is actually gonna be the VP of AM. And the VP of the right hand side is just gonna be, yes, Emma. Yeah, that's right. So the VP of the right hand side is just gonna be the VP of n squared. So now if you go here, then you have the VP similar to above. The VP of AM is less than or equal to VP of m squared. So AM has to divide m squared. Now one can check in the equation that if m divides am squared and am divides m squared for all m, that both equations are actually going to be satisfied. So what's really nice about this is that now you have a characterization, and so this is true for m, and it's independent of any other value in the sequence. So you can focus on one individual value. So now you can write. Yeah, I don't actually use Roblox though. Now you can rewrite this as a VP condition. So of course you're going to have VP of k and then over 2 is going to be less than or equal to VP of A is less than or equal to 2 VP of k. For any if A is a k good number. So what's going to be the number of choices for A in general? Number of choices for VP of A. Yeah, but essentially just the difference plus 1. But since the left-hand side is not an integer, you'll have to take the ceiling. Yeah, so the difference, so it's just going to be 2 VP of k minus the ceiling of VP of k over 2, and then plus 1. So what we need to do is, over all primes p, we need to multiply this. And then the thing is, it's not going to become an infinite number, because for any p that doesn't divide k, this is just going to become 1. So you're just repeatedly multiplying by 1 after that. So the question now is, can this actually be equal to 2019? So these are the simplifications. It's going to be either 3/2 times VP of k plus 1, or so that was a typo. It's actually supposed to be 3/2 of VP of k and then plus 1/2 if VP of k is odd. So why can't you multiply a lot of these and get 2019? Yeah, 2019 is 3 times 673. Yeah, so not divisible by 3. So both of these factors cannot be divisible by 3. So you're essentially just multiplying a bunch of numbers that are not divisible by 3. So you can't actually get 2019. Which is why so there's no k that can have 2019 k good positive integers, and that solves the question. Okay, so finally to finish with, here's some practice problems you should try. So these are 2, and there'll be 3 more. Yeah. Yeah, you can take a screenshot of these. Wait, tell me when I can move on to the next slide, because that's a few more. Yeah, so now there's 3 more. The last one is a lot harder than the rest, just so you know. Yeah, we'll do posting recordings anyway. Yeah, I'd recommend doing the UCMO 2021 one. That was pretty good. Yeah, you will have access to the slides. I didn't. Okay, that's it. Thank you. Thank you guys for joining.